next we have Aaron talking about phylodynamics via Markov genealogy processes. So is this going to be mainly opinion or results? What do you think compared to the last talk?
Results.
Results! Hurrah! Thank you very much.
Yeah. Very little opinion, although I will sprinkle a few in, I guess. I can't help it. Right, so first of all, let me say thank you to the organizers. I'm really grateful to have the opportunity to be here. It's been a fantastic set of discussions, really stimulating environment, and I'm almost beside myself with excitement for the next couple of weeks. So I want to talk to you now about some mathematical results, some quite new results on phylodynamics. And I should say that this work has been done, been massively benefited by lots of conversations with a variety of different people, some of them here in the room over the last several years, and there's been some funding here and there. So I think if there's any group that I don't need to explain what phylodynamics is, it's probably this one, so I'll just say a little bit about it. But I think of it as basically, well, it's not a very well-defined term, in that it's often, I think, most broadly used to just refer to anything that attempts to determine something of interest about epidemics using genomic data. And so there's a very wide range of different kinds of approaches in there. I'm going to focus much more narrowly. And to begin to narrow it down, I want to specifically focus on bringing information from genomic data to bear on stochastic dynamic transmission models. So not necessarily finding out who actually infected whom, but what probability distribution best explains that. Okay, so just a cartoon of that is that, we've got loads and loads of genomic data that can be used to do things like construct trees. What do these trees then have to say about the structures of the kinds of models that we use to think about epidemics? So the core problem is then one of figuring out how to build a bridge between genome sequences and transmission models to allow the information to flow. Now, there are many ways to build such bridges, and not all of them pass through the genealogy. But if we do use the genome sequences to construct genealogical trees or phylogenetic trees, and I should say I'll use genealogy and phylogeny more or less interchangeably here. If we do that, then we can construct this bridge. And so what I'm going to focus on here is this particular piece. So to say it another way, suppose we have a set of, if we have a set of genome sequences, and perhaps typically a set of time series data of more traditional kinds, cases, hospitalizations, and so on. And we've got some kind of a dynamic transmission model which represents something a hypothetical reality, which is generating these things, a hypothetical scenario for how a disease is spreading. That's typically the thing that we're most interested in. We've also got to have a model, in order to build the connection with the sequences, a model of sequence evolution. And finally, if by some means or another we can come up with a time-calibrated genealogical tree, then this is what the likelihood equation looks like, right? So the likelihood of the disease model and the sequence evolution model is basically just the probability distribution, probability density of the data, conditional on that thing. So here I'm using F as a kind of generic density, the meaning of which is clear from its arguments. And that, of course, then is just the integral over all possible genealogies, all possible phylogenies of the phylogenetic likelihood. And this is the sort of thing that Felsenstein taught us how to compute, although there's a great deal of interesting development that I think could be done here. And this other piece, which is what's the likelihood of the genealogy and the other data given the transmission model. Of course, we have to integrate that over all possible genealogies in order to get the likelihood. What I want to focus on here is this piece. So this has received a lot of attention in the literature. I think there's definitely room for improvement there, but this has really lagged behind, and so that's what I want to focus on. So the two different approaches to solving this problem, working out what's the likelihood of a genealogy given a transmission model, and these that have been widely used. So one set of them is based upon the Kingman coalescent and extensions of that in various directions, and the other based on essentially linear birth-death processes and linearizations of nonlinear birth-death processes. So both of these, the reason why these two approaches have played such a large role is that they make the problem tractable. They do that by making certain assumptions. So in particular, to make the coalescent work, we have to make some sort of a large population size, small sample fraction assumption in order to make that work. But when we've done that, in this, what's really nice is that one can think about this thing backward in time and make the calculations very tractable. But it becomes difficult and tenuous to make inferences in small populations and when the other assumptions don't hold. The linear birth-death processes are also very valuable. They, here, the tractability stems from the linearization, which makes each subclade essentially independent of all the other subclades, and that renders the problem mathematically tractable. But the problems here are that, well, linearity is, there's definitely nonlinearities in disease transmission, important ones, and so simple branching models like this struggle to explain nonlinear phenomena such as susceptible depletion, and although linearization is always possible, the small sample fraction assumptions that this requires make these things less valuable than you would like in certain scenarios. For example, at the outset of an epidemic. So what I want to ask today is how can we get rid of the need to make all of these approximations, and if we could come up with an exact method, then we would have, at least theoretically, maximum statistical efficiency. So here's what I want to do. How much is that? That thing's off by a bit, right? So I've got about 12 minutes. All right. So so in the interest of time, I'm not going to show you this first piece. I'm just going to claim that given a stochastic dynamic transmission model, it induces a unique process on the stochastic process on the space of genealogies. I'm going to show how that you can project that down onto observable data, and I'm going to present the theorem, a couple of theorems that show what the likelihood looks like for this. All right, and the full details are in an archive paper. So by stochastic dynamic transmission models, we've talked a lot about that. I think Ben on the first day gave us some ideas. Simon yesterday gave us a pretty broad definition. But what I mean, so this is just meant to be a whole bunch of different models. They're all compartmental models, and that's important. The models are discretely structured Markov processes. That's the class of models that I want to address. Okay, so here's a bunch of examples, some of them familiar, some of them more ad hoc or more specific, but we're using discrete structure to represent heterogeneities in age, behavior, strain of infection, and so on. But we all know, I think, pretty well how to do that. So technically speaking, we're going to have to assume that our population process, I'll use X for that, is a Markov jump process with some that's characterized by an initial state distribution. The probability of finding it is given by this density P0. Finding it in any place is given by this density P0, and a set of jump rates, which we can write quite generally in this fashion. So they should be non-negative and should be finite. It must be non-explosive, meaning we shouldn't have infinitely many events that happen in a finite amount of time. That's rather weak restriction. And in particular, we can have multiple epidemiological events happen at the same time. So we're not relying on this being a simple Poisson type process at all. All right, a very compact way of writing this, and one that I'm hoping to sort of impress in your mind for a little while, at least to the end of the talk, is this Kolmogorov forward equation, which just describes the flux of probability into and out of states into other states. And it's just got this simple form. There's an initial value problem here that if you can solve it, it tells you the probability of finding the system in any given state at any given time. So this is also known as the master equation in this context. So here's a very familiar model and a very generic Kolmogorov forward equation written for this. There are different rates here associated with these different transitions, and all of those are encapsulated in this alpha in some sort of form. I'll give you a more concrete form in a moment. But this isn't the only way to think about it. Another way to think about it is to think about all the state transitions that can happen, right? So if we're at a particular state here, then there are basically 5 different kinds in that model. There are 5 different kinds of transitions that can happen. We can have a transmission event, in which case the number of susceptibles goes down by 1. the number of exposed individuals goes up by 1, and so on. We can have a disease progression event or a recovery or a waning event, or we might even have a sample that's taken of some individual in the population, which doesn't change the state at all. Because each of these different kinds of events potentially has different consequences for the genealogical relationships amongst the strains, amongst the viruses, it's helpful to break them down. So here's the set of all 5 possible transitions, and to break down the alphas into the rates associated with each of these different kinds. And that allows us to then figure out how to work out what genealogy process is induced by this population process. So this is the Kolmogorov-Forward equation written for this equation, just for this system, just to see, it's not as compact as we'd like it to be. Somebody talked earlier about complexities of differential equations. It's not as compact as it might be, but it is a relatively compact way of capturing all this information. All right, anyway, so we talked about what I mean by a population process, a stochastic disease model. I need to say a little bit about what a genealogy is. So obviously a genealogy is something that relates the histories of all the extant infections in a population, which are signified by these black dots, and perhaps sampled lineages that are represented by these blue dots, and basically in some kind of a tree-like way. It's natural to represent in a tree-like way, but it represents just the genealogical relationships amongst them. So the fact that this branch and this branch have a common ancestor means that all of these guys and all of these guys were present in all of the ancestors of the viruses that are present in these guys were in the same individual at some point back there. And that's an important thing, right? So even though this represents all the sort of topological relationships, the relationships of shared ancestry, at each point along each of these branches, that viral lineage must have been in somebody. And so we actually potentially could know more about this. Well, we'll skip that. We can represent that if we knew where each viral lineage was at each point in time. We could represent that using colors. So for example, perhaps yellow here might represent being in a productively infected individual, and blue in a latently infected individual, but we could trace those things back if we knew that. But of course, this is not, well, and then there's some math. Anyway, so we won't do that. We don't have that much time. So we don't actually observe this. In fact, we only observe the samples, and so, well, sorry, I'm getting ahead of myself. So this is just some details about this. So if you look at the paper, you can see exactly where this random map from population trajectories to genealogies comes from, the key assumptions that it relies on, and some simulations that you can look at. But we don't see this. In fact, we don't see these individuals at all. We only see the samples, and so we can, through a process of pruning, project such a genealogy down to just the relationships amongst the samples, and then through a process that I call obscuring, erase the colors to get something that is more like what we actually see. So this is what we might actually be able to infer from data. All right, so let's now get the results. I want to first show a theorem that tells us the likelihood of this prune genealogy. And so I'm going to skip all the details and just state it for you. It says that if we've got a given prune genealogy, this is mathematically represented as a triple, the T being the time, the depth essentially of the genealogy, the Y being the Z being the topological structure, and the Y being the coloring, just to speak crudely. Then if we look at this initial value problem, it's very formally similar to the Kolmogorov-Forward equation, but it just differs in this little multiplicative factor here. So this piece looks just like a Kolmogorov equation, but with this multiplicative factor. There's also a singular component, so this holds at all times that are not correspond to events on the genealogy, and at events on the genealogy, there's a singular component here as well. But if you solve this initial value problem and then integrate over all possible states of the unobserved system, you have the likelihood. Of course, that's not, and this this term here is basically a combinatorical term that's quite definite. So I don't, if you're interested, I'll tell you what it is, but it's not important. It's just some combinatorics. All right, so that gives us this, but we really need this. So in order to get that, we have to integrate overall possible colorings, okay? And so that's what we've got here. So we're going to do this just through a sort of importance sampling trick. We come up with a couple of instrumental probability kernels and rewrite these terms. So basically the pi here will cancel with the pi there in these products. But again, superficially, the equation is very much like a Kolmogorov forward equation, but with a modified state process and a modified multiplier here, both a regular and a singular component. And again, the likelihood emerges just as the integral of this. So all of this looks, well, I don't know what it looks like to you. It looks pretty complicated to me. But the important thing to realize for our purposes here is sometimes this can be solved analytically, rarely, but it can fairly straightforwardly be solved using sequential Monte Carlo approaches. All right, so don't know why I put this here again. I guess I'll find out. So let's look at some examples just so you can see this. So one can apply these sequential Monte Carlo approaches in a variety of different cases. This is a case for which the exact likelihood is available in closed form, the linear birth-death process that I showed you before. So this is just a sanity check. Here there's only, right. So here is just an example genealogy that I simulated. And here are a slice of, through the likelihood surface along the birth rate direction, showing the likelihood for both the exact case and different degrees of computational effort. So one nice feature I should say about the sequential Monte Carlo calculations is that they give an unbiased, one can prove they give an unbiased estimate of the likelihood. So anyway, so that works all right. Yeah. This is another familiar example, just the SIRS process. There's the equation. This is the filtering equation written down for this case. There's only one Deem, so it's fairly easy to write this down. It's only got a few terms. But that horrible looking equation, this is what it actually looks like in a specific case. So for any specific model, it's a straightforward and mechanical operation to write down this equation. It becomes much, much simpler. I gave it to you in full generality, which is why it was fairly complex. This is the singular portion. But here's, again, another example where we've got some SIRS type genealogy, and you can see that there's quite a lot of information in the data, just here in the data. So another nice feature of the, well, I'll come back to that. And then one can do this also in the case of an SEIRS model. So this is the first sort of non-trivial case that uses, well, none of the cases are trivial, but the first case that has more than one color, right? So we have non-trivial amount of importance sampling going on here, and that's reflected in the relatively large amount of noise in these estimates. But nevertheless, one can get very good calculations, at least in this simple case. So yeah, is it time?
Yeah, you just start to wrap up. Yeah,
Yeah, I am. I'm just about done. So here's some summary. So the theory strictly extends the existing series. So both of the preceding, the existing methods are special cases of this. So it's a generalization. It eliminates the needs for these assumptions. Something I wanted to emphasize but managed to forget is that it's quite straightforward to simultaneously assimilate additional time series data at the same time that one's assimilating the genomic information. That's really, really key for the kinds of questions we've been talking about here. And the price for all of this flexibility is not necessarily small, but it's paid principally in terms of computational effort. And that, I think, is a place where more work is needed. So there are definitely some problems I've thought about in terms of things we might think about if you're interested in working on this with me, but we can talk about those later. This is basically what I told you. I think these results really help liberate us to entertain models that more closely align with our questions, and that should be useful to us. So I hope there's a little bit of time for questions.
We've got Any quick questions, please? Yeah.
So that was really cool. I'll definitely look at the paper on archive. You sort of touched on it at the end there, but this is conditional on a single tree, right? You're calculating your SMC on a tree.
Yes.
So you can embed, I assume you can embed this to jointly estimate with the tree.
Yeah.
The cost in that would be ridiculous computation. Is that sort of a
well, ridiculous may be a bit premature to say that, but you're right to be worried about it. That's this integral here, right? And as I say, I've only given you a way of computing the thing on the right, but you're absolutely right. So intelligent ways of thinking about that, or whether indeed there are intelligent ways to think about that, is a good question.
But you don't think it necessarily would be infeasible to do both at the same time based on what you've seen in the runtimes of this?
Bit quick to be pessimistic, aren't we?
I'm always pessimistic.
So am I. But yeah, fair enough.
Yeah.
We don't know. Too soon to say.
A more optimistic question, maybe?
Just briefly, have you tried this on multiple beams, on underlying data generating processes with multiple beams? And
I did show you one, yes, and I have done it on some others as well. I only showed the one.
Okay.
Yeah, yeah. You mean deems, like geographical
Yeah,
deems?
like that.
No, I have not. No, I have not. Not geographical. From a formal point of view, it doesn't matter whether the structure is geographical, behavioral, strain, or whatever. From the mathematical point of view, but it would be interesting to try on some kinds of problems like this. The scaling might be an issue.
Thank you very much. One last short question? No? Okay.
Thank you.
Fantastic. Thank you very much, Aaron.